It is important just to mention that apart from blackbody radiation, there's other types of radiation that can give you some sort of continuous spectrum, including things that you would detect in the radio. And these are non-thermal emissions. So you can have radiative emission due to, for example, an acceleration of an electron in a magnetic field. You can see the illustration just behind me. And the big difference is whether this acceleration is being done at relativistic speeds or non-relativistic speeds. So typically, at non-relativistic electrons, they are spiraling in a magnetic field. We're looking at cyclotron radiation. We can find this nearby, and I say nearby, something like Jupiter in astronomical terms. Or if you're looking at relativistic particles in a magnetic field, typically around pulsars, stars that are spinning, or quasars, which is black holes that have huge accretion disks that ionize matter and where electrons become free, and then they spiral around magnetic fields, sometimes even going out in jets. We're talking about cyclotron radiation. And finally, we can also see Bremsstrahlung radiation, specifically in the X-rays, which really means breaking radiation, the deceleration by matter. We will not be covering this a lot in Astronomy 263, but I thought it would be worth, just for completeness, to talk about other radiations beyond the black body that can give you a continuous spectrum. Finally, and just so that you understand that astronomy also uses other stuff beyond electromagnetic radiation, in astronomy, it is now becoming increasingly possible and doable to actually detect neutrinos. They're hard to detect, and there's amazing people in our department that try to do it with underground detectors in Japan, for example. But more and more, it will be possible to do astronomy with neutrinos because it's not only nuclear reactors on Earth that produce them, but stars release a lot of neutrinos, especially when they die as supernova. But even stars that are actively burning their hydrogen are big sources of neutrinos, like our own sun. Detecting them, in principle, can tell us a lot about stars dying or while they're burning their fuel. The problem, which is explained here, is that they are very difficult to detect. They barely interact with matter, and therefore we need to be really smart on how to detect it and how we can exclude any detection from being some other particles. Other sources of astrophysics information beyond electromagnetic radiation are cosmic rays, and these energetic particles are actually coming from space. We know, and we've taken pictures of it that look like this. A lot of them come from our own galaxy. Some of them may be coming from outside our own galaxy. Most of them are protons, so they're essentially nuclei of hydrogen. There are some alpha particles and some beta particles. Cosmic rays are charged particles, so their motion is affected by magnetic fields. And this means we have a difficulty in identifying the source of origin, especially if it's coming from very, very far away. It will feel the magnetic field of our galaxy, of other stars, even the solar system, and it will deflect the radiation. So it's very hard to be sure exactly where it came from. And apart from being hard to detect and interpret, they can be very annoying for astronomers like me that take long exposures, and they're looking way beyond our Milky Way, because these cosmic rays can actually hit your detector and actually produce these features in very long exposures. So we can inadvertently actually detect cosmic rays when we just expose things with CCDs. And I'll tell you more about it when we cover instrumentation. Now, 5 years ago, it would be impossible to actually do this because there had been 0 detections of gravitational waves. But since then, we have more than 100 detections that are very robust. And gravitational waves are not electromagnetic radiation. They're essentially ripples in space-time of gravitational waves. And they're caused by when you have 2 massive objects that are essentially spinning around very close, and they're losing energy through these gravitational waves. They're emitting them, and they're getting closer and closer. So because they're losing that energy. And specifically, if you have massive black holes rotating very, very fast, they can emit a lot of gravitational waves. So this was the source of the first ever gravitational wave detection in 2016. Even though this field is growing, this signal is still incredibly tiny. So it's very hard to measure and to actually explore in a wider context. And one of the main challenges as well is to understand where the signal comes from, due to the nature of the detectors. And even though we can have multiple detectors trying to nail on the position of the source, the uncertainty is still very big. So there's big campaigns of all kinds of telescopes every time a gravitational wave goes off to try to identify the source. And as you can see on my background, there's a lot of things that have been detected, all the way from very massive black holes that have merged down to things where we have or think we have identified the electromagnetic counterpart, and some kind of neutron stars merging black hole neutron stars. And this field is only going to get better. But for now, in 263, we will focus on electromagnetic radiation because there's not that many detections yet to do science, and because gravitational waves mostly deal with the end states of stars, which you will actually study in your third year astrophysics module if you take it. So all done getting to the end of part 1 of section 4, that's up to section 5.4. I'll just leave you with a summary of things that you should now know about. I would encourage you to read the lecture notes if you haven't, and also try the questions at the end, specifically those that will correspond to sections 5 to 5.4. And when you're done with this, I would encourage you to jump into part 2, where we're going to be talking about line spectroscopy and how we can use the Doppler effect, for example, as a superpower, and how we can explain the widths of lines that we can see from astrophysical objects. So I'll see you for part 2.